Siamo live? Siamo live. Sì. Partiamo? Vado. Okay, we can start the second part of the session. So, ask you the next speaker, Martina Cardillo, here.
Questo no?
Questo che aperto.
Ok, perfetto. Basta.
Tutto buono.
So, good morning everybody, I'm Martina Cardillo and I am a postdoc at the National Institute of Astrophysics here in Rome. And today I talk about the love story between cosmic rays and supernova remnants. So, the first question is obviously, what are cosmic rays? Cosmic rays are very high energy particles, mainly protons, that reach us with a very energetic spectrum and with a power law distribution. So this power law spectrum has a lot of features very important. The first one that you can see is a banding at the lowest energies due to solar modulation. Then cosmic rays follows a power law with an energy index of 2.7 in energy. That is an index that is the sum of an ejection index and a diffusion index, because obviously cosmic rays come from the source to us on the Earth. Then we have the most important feature of the spectrum, that is the cosmic ray knee at about 10 to 15 electron volt. And the name knee is due to the fact that after this energy we have a steepening of the spectrum, and this feature is very important also because divided the galactic component of cosmic rays from the extragalactic component. Okay, this presentation is focused on the galactic component, as you can see in the following. Then, after the knee, we have always a power law with a steeper index of 3.1 in energy, and up to the last feature of the spectrum, that is the ankle, at more or less 10 to 18 electron volt. Okay. So we have these high energy particles composed mainly by protons that are galactic up to energy of 10 to 15 electron volts. So the first question is, which mechanism can accelerate these particles up to these highest energies? The mechanism is the first order Fermi acceleration mechanism. What is it? So we have a shock on a source, in an astrophysics source, and we have injected thermal particle with some threshold energies that are reflected back and forward the shock due to magnetic perturbation that we have in a shock of a source. And with this mechanism, the particles gain an energy proportional to the ratio between the shock velocities and the speed of light. And the name, the first order Fermi acceleration, the name is due to this proportionality. And another important feature of this mechanism is that it provides, in the simplest way, a power law energy spectrum, so the one that we observed at the Earth. A power law energy spectrum with an energy index of 2. If you remember, I said that this is the injection spectrum, and D becomes a 2.7 when cosmic rays reach us after diffusion in the galaxy. Okay, so this is the mechanism, but what are the sources of the galactic component of cosmic rays? So the scientific community is in agreement to think that the galactic sources of galactic cosmic rays are supernova remnants. The first reason is an energetic one, because only the 10% of the supernova explosion energy is sufficient to explain the cosmic ray energy density in the galaxy. Then we have obviously a shock during the shock propagation in the interstellar medium, and so we can have in a very simple way the Fermi acceleration mechanism. And again, we have indirect evidences in the X-ray and optical band. However, these indirect evidences are not sufficient to be sure that we are seeing cosmic ray acceleration in these kind of objects. So we need to search for direct evidences. How we can do this? We can use the gamma ray astronomy. Why gamma ray astronomy? Because cosmic ray proton can interact with a proton of a target, interstellar medium, or molecular clouds that are that have very higher energy with respect to interstellar medium, and produce a pi zero. This pi zero decays into gamma ray photons. These photons are very important because they have no deviations from the source to us, so we can reconstruct the direction of the source in a very simple way, and they have the same spectrum of the parent population, obviously with a lower normalization, and the energy of the photons are more or less the 10% of the proton energy. So we have a lot of information from this channel, this information channel. So, which are the evidences for which we are looking for in the high energy astrophysics? The first one, and we don't talk about it, but I want to show you this because this is our future with the Cherenkov telescope array that you have for sure feel the name. And so the first evidence is at the highest energy of the gamma ray spectrum, because if we need to be sure that we have near cosmic ray protons, so protons with an energy of 10 to 15 electron volts, because of the fact that photons have 10% of the energy of the proton, we need to detect 100 TeV photons in the gamma ray spectrum. Up to now, we have no sources, no supernova remnants with photons at this highest energy. And we hope that CTA, the Cherenkov telescope array, in the future can answer to this question. But the other evidence, the one that I tell about now, is at the lowest energies. In fact, the fact that the pi zero decay into gamma ray photons forms this feature in the flux spectrum of the gamma ray. So we have a pion band at half of the rest energy of the pi zero. And this kind of feature transforms in the spectral energy distribution in a kind of decay below 200 MeV, more or less. And this kind of behavior is the only way that we have to distinguish the hadronic gamma ray emission from leptonic gamma ray emission. And we need to distinguish it because only the detection of hadronic gamma ray emission gives us the certainty that we are seeing cosmic ray protons from supernova remnants. From this point of view, in 2011, we have a breakthrough because we thanks to the Fermilab and then to the Agile, an Italian mission satellite, gamma ray satellite, we have so this kind of this remnant that is the W44, is the gamma ray image with the radio contours, that is very bright in the radio and in the gamma ray band. And from this source that is interacting with the molecular cloud, so if you remember, we have a higher density, so we have a lot of target protons to do our PP interaction. For the first time, Agile can detect the decay, if you remember the previous slide, the decay below 200 MeV. So for the first time, we have the evidence that a supernova remnant is accelerating cosmic ray particles. 2 years later, also Fermilab confirms these results thanks to an improvement of their software. And so this is a very important result for energy astrophysics, even because other two remnants that are very similar to W44, Z443 and W51C, were detected by Fermilab below this energy threshold. But now, in this enthusiasm, general enthusiasm, for having find this hadronic evidence in a supernova remnant, also the scientific community tried to develop acceleration model in order to fit data. But we have problems. Which problems? The first problem is that all the acceleration model provides a low energy cutoff and a breadth in the energy spectrum that are not in agreement with the diffusive shock acceleration theory. So they are not easily understandable in the theoretical context. The second problem is that in this kind of sources, so the three that you have seen in the previous slide, we have a very slow shock velocity because these remnants are middle-aged, so they have an age of about 10,000 years. And for this reason, for this reason, we need a too high cosmic ray efficiency in order to explain the gamma ray spectrum. So for this reason, we thought that maybe we are not seeing acceleration of cosmic rays, but reacceleration. What is the difference? The first important difference is in the injection spectrum. In the case of acceleration, we need a thermal particle injected at higher energies with unknown mechanism because it is related to microphysics that is not so known in the energy astrophysics. Instead, in the reacceleration, we have the known spectra of pre-existing cosmic ray particles in the galaxies, okay, from Voyager data. The mechanism is the same. We have always the first order different acceleration, so the reflection in the shock of a remnant. But the effect of the spectrum is different because in the case of the ejection spectrum, we have the spectrum of an index gamma p in the momentum spectrum. Instead, in the case of reacceleration, we have two kinds of modifications. In the case the pre-existing cosmic ray spectrum is harder than the index due to compression ratio of the shock, we have the same parent population spectrum. Otherwise, we have an hardening of the spectrum. Again, we have, like in the acceleration, a cutoff energy at the highest energy due to the fact that the acceleration time has to be less than the minimum between the loss time, obviously we have a lot of energy losses at these energies, and the age of supernova remnant. And finally, we have a different normalization depending on the compression ratio and also by the initial normalization of cosmic rays. So, we developed a lot of reacceleration models. So the first reacceleration models use this kind of consideration. So we have a persisting cosmic ray spectrum, but in these years we have only the solar spectrum of cosmic rays. If you remember, the solar spectrum of cosmic rays is modified by sun, so it's not the real galactic spectrum. And again, we have also a compression of the code, because if you remember, I said that W44, like also the other remnants, are interacting with molecular clouds. So we have a further compression in the cloud. So we have a thin, hot layer of the cloud where we have a further compression. But these first models have again problems because again they need of low energy cutoff or of a breadth, and they not consider energy losses or no secondary particle because we have also secondary electrons from the PP interaction. Okay, so in 2015 we have the luck to have the first data of the very interstellar spectrum of cosmic rays, so outside the heliosphere, because Voyager came outside the heliosphere, and using this data and considering particle losses, considering the secondary particle spectrum and contributions, and emphasizing the simple powerless spectrum without no steepening, without no breadth, but only with the high energy provided by the physics of the system, we were able to fit the W44 gamma ray and the radio spectrum. So maybe reacceleration is the explanation of the gamma ray emission from this kind of sources. And not only because we, in following words, we have seen, okay, thank you, we have seen that reacceleration can explain also other kind of gamma ray emission. For example, here you can see in excess in the gamma ray emission from the Agile satellite. So we have subtracted the background, the gamma ray background, and we highlighted this excess that is in correspondence of a star-forming region around the K-Oris OB star in the Orion constellation. And this excess can be again explained in a very simple way with reacceleration. So maybe also a forward shock of a young star like K-Oris can produce a cosmic ray through reacceleration. Again, reacceleration can explain also other features. I have no time to explain them in details, but I want only to highlight that the reacceleration can explain some features, some tricky features in cosmic ray spectrum of in the particle, spectrum of cosmic rays, and can also modify the inclination of the shock. So what it means? It means that in the simulations, seems that only a parallel shock can accelerate cosmic rays, but the presence of reacceleration can modify the inclination of the shock. So all the shock can accelerate or energize cosmic rays thanks to the contribution of reacceleration. So, which are my conclusions? My conclusion is, okay, we now know that supernova remnants can energize cosmic rays. Maybe the middle-age supernova remnants can do this only with reacceleration, not with acceleration. That is, however, the main mechanism for which we can see cosmic rays here. But if we have the conditions in a source to have acceleration, we always have also the reacceleration. So when we do research, we have to be careful with the fact that we have to avoid that the Einstein sentence for which the theory which decides what can be observed. No, what we have to do, and Einstein said the same, is that we have to analyze data. We have to use the Occam Razor's law. So the simple way to fit data, and only then, and only have to do this, we can interpret the data. And it's all. Thank you very much.
Thank you, Martina. Are there any questions? If not, I have a couple of more curiosities. First, if in the scientific community now, because of the reacceleration model works quite good, if pure acceleration model are now completely discarded. And second is if the last model of acceleration has still some open questions. Something that is not completely understood.
Regarding the first question, obviously no, because here we have middle-age supernova remnants, so old supernova remnants with a low shock velocity. But maybe, and we hope that also CTA can answer to this question, young supernova remnants, for young I mean 100, 200, 300 years, okay? They can accelerate in cosmic rays. So the acceleration is the main mechanism for in order to have these kind of particles. But the fact is that reacceleration is present, so we need to compute the contribution of reacceleration in all the sources that we studied. And so this is the first question. The second, there are a lot of open issues. Yes, a lot of open issues, because obviously we need to have confirmed that yes, this theoretical model effectively sees the reacceleration, because yes, but these are theoretical models with a lot of issues, a lot of parameters, but we have a lot of microphysics parameters that we have known. So yes, we need to have more instruments. For example, in my opinion, there is a problem, because in the future we have a CTA, for example, at the highest energies, but when Agile and Fermilab handle their mission, we do not have in program any mission at the MAVGV energy band. And in my opinion, is a great problem, because a lot of issues like cosmic rays Still, yes, they keep open because we have no mission in the future, programming in the future, and this is a very big problem.
Why do you think agencies are not handling this kind of missions?
This is a kind of question. So I really don't know. I really don't know because I'm in obviously in some proposal like YAS program that is one of the mission proposed in this band, but I think that maybe the fact that we have a lot of manpower in CTA and the gamma ray with CTA, so maybe the scientific community think that it's not so important that this energy band, but I really don't know why they think so. I really don't know because I think that there are a lot of issues linked to these energies. Because again, we have now Agile and Fermilab are keep working, but from I think that 1, 2, 3 years and then I don't know. I really don't know. I don't know how to answer this question. Really.
Thank you.
Thank you.
There are no more. A question.
Thank you. I was wondering, at the tail of the distribution, the higher energy, why does it deviate the experiment from the why does it deviate, like
the hardening?
Yeah, it continues down in the model, but the experiment flattens?
Yes, this is due to the fact that at the so-called cutoff energy, we have no reacceleration at all, but we have only compression. So the spectrum has changed because we have only the compression in the cloud, if you remember the model, but we have no reacceleration because the reacceleration time is higher than the time scale of the system. This is the okay. Thank you.
Okay, one last question.
I can see this spot with the boron hardening.
Yeah.
This is very interesting because EMS measured that most of the nuclei are hardening. And so this model is able to...
Yes, to explain all the hardening of all secondary nuclei. Is the Pasquale Blasi paper in 2017, if I remember well. It's very interesting because it seems that it can explain all the secondaries hardening of the spectrum. Not the primary, but the secondaries, yes.
Okay. Thank you very much.
No, you're welcome.
Okay, thanks Martina again. Thank you. We'll move on to next speaker, Federico Tosone.
Hello everyone, I am Federico Tosone, a PhD student here in Rome, and today I want to talk about cold dark matter simulations because they are an important tool that we need in cosmology. So first of all, let me start from basic definition, because maybe not all of you know cosmology. So one common definition of cosmology is the study of the universe as a whole, because we believe that the universe is a closed system. So once you give initial conditions, the universe will evolve in a very specific way. And the basic idea in the standard cosmological model is that at the beginning, you have inflation, and there are quantum fluctuations for all the components in the universe. So baryons, matter, radiation, they have quantum fluctuations. And we think, actually, we know today that a Gaussian random field can fit very well these quantum fluctuations. And we also think that in the standard model, these fluctuations at the beginning are the seeds for structural formation. So they will start accreting matter because of gravity, and structures will form. So we will have galaxies, stars, planets. And today we have another question that is dark energy, because the universe started to accelerate today, very much like the initial inflationary period, but we don't know why. So there are various branches that you can study in cosmology. My interest is, let's say, in the middle part, in the development of structures, because, so this is the pie chart of the energy content of the universe. And as you can see, only 5% is made of baryons, of luminous matter. Then there is 70% which is dark energy, and we don't know what dark energy is. And finally, there is dark matter, which is what is the driving component for the formation of structure. Now, when I say structure, I don't mean exactly galaxies, but I mean the dark matter large-scale structure, on top of which galaxies and stars will form. Now, so what we try to do in cosmology is try to estimate the probability distribution function of matter, because this contains information of how the universe evolved. This contains information about the law of gravity that is ruling the universe. So let me give you some definition first. So we need an overdensity field, which is just the relative overabundance with respect to the background average. Then we have the two-point correlation function, which is telling you how much we have an excess or a defect of probability with respect to a uniform distribution, that given a particle at a position x, we will find another particle at a position x plus alpha. And its Fourier transform is the main tool that I will focus on today, which is the power spectrum. It's just the Fourier transform of the two-point correlation function. And it tells you the amount of structure, quote unquote, that you can find at scale k to the minus 1. K is a wave vector. So once I define this tool, I can go on. So I told you about quantum fluctuations. Now, what we try to do in simulations, for example, by taking an n-body code like this one, this is gadget, we give an input power spectrum to the particles. So the particles at the beginning are on a uniform field. We give an input power spectrum, which means simply to assign an overdensity to each particle. Then we solve the Poisson equation, so particles will be a bit displaced, and then we evolve the system using gravity. So these particles, these are cold dark matter particles, which are interact only through gravity, so there are no collisions. And I'm showing you the initial snapshot of the simulation. As I move on in the simulation, now the redshift is changing, so we go to lower redshift, so we go to later epochs, and the structures start to, let's say, start to form. And finally, today, at redshift 0, we can clearly see what we call the cosmic web. Now, the cosmic web is this bunch of structure, of cold dark matter structure that form. For example, the knots, these clamps, they are halos, while the lines are filaments. So this is what so this picture here is basically the theoretical expectation that we have for the distribution of galaxies. Now, here we have just cold dark matter. I didn't add any variant, but what people do to make contact with observations is to add galaxies on top of this picture and to compare the distribution of this picture with the picture that we have from images, from data. And this is the power spectrum that we get from the simulation. So the red line is the input power spectrum rescaled to the present time, while the blue line is the power spectrum from the simulation. So as you can see, there was an evolution. There were no linear interactions between the particles. So the input power spectrum changed into something else, which is not Gaussian anymore. We don't know what it is, and we are trying to constrain it. That's what we are trying to do. But there is some nonlinear process which is hard to understand. So the main problem with n-bodies is that they are the only truths that we have about cold dark matter. But at the same time, they are black boxes. So we don't know what is happening inside. So it would be nice to develop semi-analytical tools to try to, I'm not saying predict, but at least to understand the blue line of the power spectrum. And this is what, let's say, I've been trying to do. So let me start a bit of, let me tell you a bit of the formalism of Lagrangian perturbation theory. So the starting point is to approximate cold dark matter, so these particles, as a fluid. So this is just an approximation. It will not be true at all the times, but initially, when the field is linear, it will be a good approximation. And we are trying to solve for the displacement field. So the Vlasov equations, I don't know if you know what they are, but they are telling you how the phase space distribution of particles is evolving. Under the approximation of a collisional fluid in an expanding universe, they just reduce to the master equation here where we have the Hubble drag, which is a friction term, and the cosmological potential. And what we want to solve for is psi, the field. Now, in a Lagrangian picture, you are telling each particle where to go. So you may know this metaphor. Euler is standing on the bridge and is watching the river flowing, while we are Lagrange, because we are moving on the boat alongside particles. In order to solve this equation, I mean, this can be done in a perturbative manner. And for example, I'm just, for the sake of simplicity, I'm just writing the first order, but you can go to higher order. This is the first order solution for this cosmological fluid. And well, this equation is very simple, but it is nice because it's showing you something quite intuitive. For example, if this is positive, if delta, the initial over density that you give as an initial condition in the simulation is positive, you will have that the divergence of the displacement is negative, which means that particles around will be attracted. And the contrary is true. I mean, if delta, the initial power spectrum, is negative, it means that the flux will be outward. So you have that there will be a void. And the velocity of this particle will be parallel to the gradient of the potential, of the peculiar potential. Now, so this is just to tell you that once we have an initial, an input power spectrum, we can solve for the displacement, and we can go an analytical simulation, which is very fast. And for example, so this is the embodied, which I showed you before, and this is the analytical approximation that I just explained, which is called the Zeldovich approximation, and it's very famous in cosmology because thanks to this we had an analytical understanding of the cosmic web for the first time. As you can see, it's not perfect. Clearly, we cannot compete with an embodied. And indeed, if we compute the power spectrum, we have this red line. So it's far away from the yellow line. The yellow line is the exact true solution. But at least we recover at linear scales, we recover a Gaussian field. So it means that the universe on large scales is still behaving as a Gaussian random field. But at this point, there will be shed crossing, so particles will start to overlap, and this approximation will not be good anymore. Now, what I've been trying to do is to try to improve over this red line, and I do this by using the halo model. So the halo model is a very simple smart idea. It's a toy model, which is telling you that all particles in the universe are found as hard balls. These hard balls are realized structures which are called halos. And the basic ansatz of Peacock and Sajak was to say that the power spectrum can be split into two terms, the two halo term and the one halo term. Now, the two halo term is telling you the correlation between particles belonging to different balls, belonging to different halos. While the one halo term is telling you the correlation between particles within the same halo. Now, the two halo term is something that we know because we think is this blue line, the linear theory, the input power spectrum. So we are saying on large scales, the input power spectrum is a good description of where halos will be, while the one halo term is a complicated function of the Navarro-Franken-White profile. Now, the Navarro-Franken-White profile is also a very famous result in cosmology because it's the profile of particles inside, it's the density profile of particles inside an halo. So, knowing this, I recast this I try to make the parallelism between the power spectrum, the halo model, and the Lagrangian picture. So, I simply say that the displacement of particles will be made of two parts, the two halo term displacement and the one halo term displacement. And we can say that the two halo term displacement is well approximated by the Zeldovich approximation, which is the first order solution, so to mimic the linear theory, while the one halo term is given by a displacement of particles following the Navarro-Franken-White profile. And I also need an interpolating kernel, so this is just a smoothing kernel which will depend on some scale to make the transition between the two regimes smooth. And if I do this, I also need to find the effective remapping of particles. And this is easy to do because I just need to say that once in the initial conditions I find the location of an halo, I have to say that all those particles at the end of the simulation will be displaced according to an arrow of left and right. So this is, in principle, it's easy to do. Now, the other question is something else, is to find halos in the initial conditions. And this is also a very old idea in cosmology. It's one of the most fundamental papers in cosmology by Bartin, and it is called the peak bias formalism, where you say that halos will form in the maxima of the initial density field. So you have to just locate all the maxima in your initial density field. And once you do that, you say you have to apply some criterion to choose which of these maxima will be a good halo candidates. And the criterion that we have is the spherical collapse model. So you just move the field over some scale, and you say, okay, if this field has a value over some threshold, this patch, this halo patch will collapse to form a real halo in our simulation. And now we'll show you the results of this toy model with the Lagrangian feature. So this was the Zeldovich approximation. This line here represents the power coming from halo particles alone. Now, if I simply sum these two curves together, I will not get the nonlinear power. So I need to interpolate between the two, and I get something which is qualitatively resembling what we have from n-body simulations. So this is just a preliminary result. I'm still working on it to make it more accurate, but this is the main idea. And yeah, so maybe I was fast, I don't know. This is just to conclude that I have presented you a new dark matter simulation scheme inspired from the halo model that helps us recovering the power spectrum of smaller scales, and it is an insight into the nonlinear structure formation. Thanks.
Thank you, Federico. Is there any question? One.
So thank you for the nice presentation. I have a question, please. Does the model scale down to smaller scale? Like if you consider the infinite universe, you get some results.
Yeah. Of course, there is a dependence on the box. So even if you apply periodic boundary condition, you have still a limited box, and this will influence the, let's say, the linear power. So the point is that the power that you have at linear scales will affect the nonlinear power. So in principle, the bigger the box, the better is the simulation. And this is a challenge. This is a challenge for the embodies. That's why if we have an analytical tool, it's better, because with embody you have to have a box as large as possible, and we are limited by computational resources. But yes, it depends on the size.
And more or less, do you know any behavior how the?
Yes. So if you have a smaller box, you will have less power on linear scales, and this will screw up also the nonlinear scales.
So if scales with a longer even?
Yes.
One question, yeah.
Do you compare these analytical extension results that you get with some simulations?
Yes. I mean, more than this, I mean.
So, can you just explain this thing again?
So the embody is the yellow line. So it is the real simulation, while the black line is what is coming from my fast simulation scheme, so from the analytical approach. But really this is not a proof that it works. You have to do some cross correlation with the embody to make it, let's say, a solid result.
The green one is the halo profile that you...
Yes, this is just the one electron contribution.
Okay.
Yes.
Okay, last question.
Thanks. Do you have some insight about why the distribution stops reduction exactly at that point? I mean, is that a relevant point, a relevant power?
What do you mean, the lines?
No, you did in the picture you were looking at. Yeah. I mean, the decay there, the decay when the distribution. No, for example, the yellow one.
Oh, okay.
The Gaussian in the beginning and then it deviates.
Yes.
Okay. The point where it deviates.
Okay, that's the point where non-linear structure become important.
Yeah, physically.
And that's the problem. We don't really understand what it is. But basically, it means that you will have spherical collapse, and this is a nonlinear interaction. And that's the basic understanding. But this is one of the most open problems in cosmology, to try to explain this increase of power at k equals 0.1. Yeah.
Okay, thank you.
Okay, we can thanks Federico again. We move to session speaker by Sandeep Paridas.
Hello everybody, I'm Sandeep. I am currently a postdoc at the University of Rome, YRM. Today I'll be speaking a bit about the phenomenology of dark energy, which is one of the other dominant components involved in the late time evolution of the universe. So, in principle, I'll go through some introduction, which I hope is going to be useful to understand the later things. So, the current framework of cosmology, of the underlying theory behind gravitation, is coming from Einstein's general relativity. And this has been a very successful theory for over 100 years, in fact, even being validated by the most recent gravitational waves observations. And it's in principle the only theory that's working well enough today. So the idea here was simply to say the curvature of the space-time is in fact equivalent to the effects of a gravitational force that one would see in a Newtonian way of looking at the matter distribution. And so Einstein had simply an idea to write down, not simply, but okay, it's a good idea, to write down the curvature on one time, which is basically the geometry of space-time, and the content of the universe, which is now going to mutually affect each other to change the space-time's curvature according to the amount of the content, and the content can actually be known or understood by looking at the curvature of the universe. So basically having the two components equated to each other. And having an initial understanding or initial expectation to have a static universe, there was the phenomenological constant introduced into the field equations by Einstein himself, which were actually supposed to stop the universe from expanding, which was what was coming out of the field equations. And then later it was very much dropped, given the observations of Hubble in 29, that the universe is actually expanding and it's not a static scenario. But however, later in 98, which is almost after 70 years, that we reintroduced cosmological constant, now that we understand that the universe is actually accelerating at late times. So this has been a great re-entry of something that was supposed to be a mistake, but in fact it's not, for a good reason that we will have to understand even better. So, what is the modeling that's involved with this framework anyway? So, we want to have some sort of a very symmetric way of looking at the universe, because we know it's quite isotropic when we look at it in different directions. And being isotropic, we would also expect, not being in a special position, we need homogeneity. And homogeneity and isotropy put together are actually forming the cosmological principle, based on which we have a metric that is a solution to field equations. And then we can actually write down the evolution of the universe itself in terms of this quantity that's called the scale factor. And the rate of change of scale factor and the double derivative of time, which is going to give you the rate of change of the expansion rate itself, so which is the acceleration of the universe. And these things are simply dependent on the content of the universe, the curvature of the space, the pressure in the second term, and so on. And basically all the components of the universe and everything we have inside. So these things can be simply rewritten by defining somewhat more convenient parameters, which is basically the equation of state for each of the components that goes into the evolution of the universe. And then we define the Hubble parameter, which is simply the relative change of the scale factor. So what are the components of the universe that we know of? So we know that, So we know that there are photons, which are like very well known, probably the least of the components that we have to worry about. And then we have the baryons, which are also quite understood, and we know the physics of the baryons. Neutrinos are pretty much there, while they still have a lot of physics that needs to be explained and understood. Well, they could make a bit of a difference, maybe with better observations. But then we have a couple of hypothesized contents that we want to have in our universe. So one of them is the dark matter, which was luckily very well introduced by Federico. So we wanted to hypothesize the dark matter because there was a clear disagreement between what one would expect in the rotational curves of galaxies based on the content of the galaxy itself, the mass of the galaxy itself. So the luminous matter was very much not sufficient to explain what we see in the velocities. And so we hypothesized the cold dark matter, which is the second most dominant one. And then we have the dark energy, which is the most dominant component today, or in the late times in the universe. And this was pretty much the result. So for example, here in the open contours, we see the very first discovery of acceleration using the supernovae dataset, which I will arrive in a couple of minutes to explain a bit better. And here we see actually the improvement in the statistics of acceleration itself, at what rate we now constrain acceleration and how sure we are of having this acceleration phase. And so this is the component, the equation of state of the cosmological constant being -1 is the component that is actually driving the expansion of the universe in an accelerated fashion. And that is a phenomenological inclusion as well. It's just hypothesized to be there because we want the universe to accelerate, and it is supposed to be -1. But however, there is quite a good amount of motivation to go beyond -1 and to actually see if the equation of state has some sort of dynamics to it. Firstly, because we really don't understand what exactly -1 is and what kind of physics is underlying. So there is no consensual theory that's being able to propose and predict a W equal to -1 in a consistent way or a satisfactory fashion. And so it's quite a good thing to investigate. In fact, there is a dynamical evolution of the same. So, just to summarize, we have the Friedmann equation now with all the components, and depending on which of the component is dominating at which time, the universe will expand in different fashions. And whenever omega lambda is dominating, we have the acceleration. So, we have different models that one can summarize. And this is a very usual way of testing for dynamics of that energy. So we simply want to do a Taylor expansion around W of Z, supposedly varying in time kind of equation of state. And that's basically the most utilized one. And so what are the observables that really hint or give the evidence for late time acceleration? So like I was saying, the supernova were the first ones, and in fact, today they are the best observables that give us evidence for acceleration. Pretty much because what we expect from supernova is that they are supposed to be known objects of a particular kind of explosion that happens towards the end of the life cycle of a star, and they are basically supposed to happen in a similar fashion, which is now allowing us to simply measure the distances or estimate the distance to a given supernova, knowing what is the observed luminosity of that particular supernova. And so these really are the best sources, which are cosmology independent and give us the acceleration. While it's no longer the case that supernova are the only observables that give us acceleration, because we have on low redshifts what we call the baryon-acoustic oscillations, which are basically, once again, the dynamics between baryons and photons of early times, which are reconciled with the structure that we observe at low redshifts. And in fact, a bit of dark matter phenomenology goes into understanding what exactly is happening there, without going into details. BAO is also confirming a good amount of, it was also confirming and aiding with a good amount of evidence that there is acceleration. And finally, I'll use, or we have another observable, which is basically tracking the age of the universe in that shift. And so knowing the age of the universe, which is now simply going to be translated to be the rate of change of the scale factor with respect to the rate of change of scale factor with respect to itself, which is the Hubble parameter, we actually have these very nice observations which are completely model independent. And in fact, we can track what is happening to the expansion of the universe in this low redshift phase. So having these three observables, which are the most constraining ones for the dark energy phenomenology itself, I would like to enter into what exactly we do for, let's say, a phenomenological study. So, in principle, so far one could have simply utilized one of these cosmological models. So, these models are going to give you the expansion history, for which you have particular reasons why you define a particular model, a simple lambda CDM, which is a standard model, or certain extensions, which are once again additional parameters that you want to test and fit. But this is still a very model independent scenario where you do find some sort of a bias that is introduced by what you are assuming to begin with. So in principle, we in the very initially we implemented this model, implemented this analysis based on something we call Gaussian process, which is basically a very simple extrapolation of whatever is the Gaussian distribution. So one would expect that if there is a Gaussian distribution for, let's say, a particular functional form, a particular observation, whichever is it, a mean and a distribution around it. Now we want to model what is the covariance between two such observations. So I would like to have a number of observations which I'm expecting are actually outcomes of a given multinormal distribution. So all these observations are supposed to be somehow correlated, which is actually modeled by the covariance between one observation and the other observation within the same observable, of course. And we do this by assuming a particular functional form for the covariance itself, which is in a very simple way is simply a Gaussian, so it is called a squared exponential in principle. And we can have a more flexibility that can be introduced into this modeling through a bit more of a complicated model, but very much more flexible, while not losing the power of prediction, because we do not have additional parameters. So we have these modeling, we have these assumed covariances, and towards the end, what one has to do is simply fit for a marginal likelihood, either in a Bayesian way or in a frequentist approach, having these hyperparameters that define what exactly is the covariance. And that must help us to actually arrive at something we call a reconstruction. So in principle, what I'm showing here is a combination and a collection of supernova data sets here, which are actually compressed to be put in the form of an expansion history here. And here we have the Bayesian acoustic oscillations, and here we have the H of Z observations. And in principle, we did a kind of a model-independent cross-correlated analysis, where one would like to actually understand what is the underlying expansion history. And this curve, which is like unique expansion history in all these data panels, is in fact a model-independent reconstruction. As in, we do not have a cosmology that is pre-assumed. And so what I would expect is that this could in fact be my expansion history without introducing any biases through dark energy modeling or dark matter modeling or in fact anything otherwise. So having the reconstruction of the H of Z, one could actually then look for what exactly is the underlying equation of state. So in principle, as I was mentioning before, we have the W equal to -1, which is actually the standard lambda CDM model. And this is the reconstruction that we obtained from what exactly I showed you before. So having this expansion history, the underlying W of Z would actually be this. And here I'm actually trying to validate the method through another independent method, which is actually done by doing a Taylor expansion, which I mentioned earlier. So in principle, you do find some sort of similarities. There is a good amount of agreement between these two methods. But of course, it might very well be that both these methods are biased in their own way because of the assumption of the expansion itself to what order truncated, or due to the assumption of the kernel itself. But then there's still something still very useful to predict something phenomenologically and see if there is a deviation from W equal to -1. And luckily, we don't really find any, not luckily, but as yet, we do not find any strong deviations from W equal to -1 at this point. And later, we also started exploring some other techniques which are supposed to be even more flexible, just to not have the simple biases that I would even expect to have. Essentially, to say you want to have a very flexible method while having extremely simple way of modeling it. So it cannot be flexible at the cost of having complicated modeling. So it has to be both flexible and simple. And so we implemented some sort of simple interpolating schemes by actually having a well-defined prior region within which I would expect my equation of state to lie. So here I'm actually showing you the energy density itself, which is supposed to be 1, and deviating from 1 would be dynamical behavior. So having this, we actually, once again, reconstruct the energy density of the dark energy. And the current data is, in fact, not necessarily showing any deviation at the lowest regions, lowest redshifts, but we do find some amount of mild, which is in 1 sigma green with the cosmological constant scenario. But then there are, of course, differences which come due to the kind of assumptions you make about which quantity you're actually modeling. So if you in principle model the equation of state itself, this is what I find, having no deviation at all, but a probability that there might be something that's going towards a deviation at higher redshifts. While in the case of modeling the energy density itself, we actually see that there is really nothing to see, at least today. And so this actually is validating that the cosmological constant is probably the underlying physics. Well, of course, we have to understand what is the physics itself that gives rise to that. So it really is a consistent picture. And at the same time, if you try to do a reasonably different modeling, like you want to change the way you want to give your priors, basically to say, maybe I expect something more smoother, or I expect something to have more features, you can actually find some sort of deviation. And in fact, I can increase the deviation if I want to, but it's not what you want to do. As in to say, you have to still validate what exactly is the best scenario that you're constraining. And so there is still a bit of an open question here, as in what is the better way to understand the phenomenology to begin with, and hopefully to understand the phenomenology so as to put some constraints or to understand what is the physics itself that we have. And clearly it will be very much benefited by more updated and constrainable data, more stringent data that will come in the near future. Thank you.
Thank you, Sandeep. Are there any questions? Okay. Curiosity about your work. You told there are still other open questions about what is the best way to understand the phenomenology of dark energy.
Yeah.
What is your opinion about, or what are the next steps of this work?
I mean, my opinion would be that, so if you take one method and try to do a reconstruction or study the phenomenology, you would find something, but clearly there are assumptions that are going into this method. Right? Okay. So to cross-validate these assumptions that are going into independent methods, you would want to have complementary methods. So let's say you want to do phenomenology in 3 different ways, and then validate all of them are giving you equal prediction. So for example, here I'm saying these 2 methods give a similar prediction, but in principle, this guy doesn't give the same prediction. And that's because the way it's being modeled here with the assumption of this Taylor series, which is cut off at a certain expansion, the series expansion, and this as an assumption of the kernel, let's say. So there would be some biases. So in principle, you would want to validate this reconstruction against this reconstruction, let's say, to understand which is the one that is actually being better. And it's not just about having a better chi-square in the end. You don't want to fit everything very well and say this is nothing. Instead, you have to penalize the method for the amount of flexibility you give. So you have to cross-validate between methods.
Thank you. If there are no more questions, we can thank Sandeep again. The session now is over, just service information. Okay. Service.
Okay, now some guys will come here and introduce the villa to us. We will start from here with an overall introduction, then we will go outside and take the group picture, and then we will split in 3 groups, and we'll go for a tour of the grounds. So, okay, the guides are about to come, so be patient.
Just an announcement for the speakers of the next session after 9. lunch break. Since I will be the chair of the session, I need the presentation to be uploaded on the laptop that we are using. So please bring your presentation now or during the lunch break here to process. Thanks.
Io direi che questo lo stoppiamo.
Dunque io devo